personal stylist. Especially in recent years, being a teenager and all, she's always asking me what's the new trend and what's in right now. Don't even get me started when she's prepping herself for a night out. Sometimes it can take her up to an hour and a half to choose what she's going to wear. Don't get me wrong, I love my mom, and I want nothing more but to help her pick out the perfect outfit for ladies' night. But this task just takes too damn long and is so tedious. Now, it's not like I can see all of her outfit options at once. She has to put on the outfit, find the right accessories, spend about 10 minutes looking at herself in the mirror, then get my opinion, and then we repeat this process 15 times over. Now, even though my mom's problem is figuring out what to wear for the night, this exact scenario is what is causing some of the biggest inefficiencies in the drug discovery process. See, this repeated process of trial and error that just takes so long and half the time doesn't even get us to the right answer. See, the most inefficient part of drug development is the initial drug discovery process itself. See, during this first phase, researchers test thousands upon thousands of different compounds to see how they react with the disease in question. But this process can take up to 5 years to complete. Now, there have been classical algorithms that have tried to fix this problem, but the inefficiencies remain because classical computers just don't have the computational power to solve this problem. Not to mention, simulating really complex molecules on a classical computer is virtually impossible to do. But this is where quantum computing comes in. See, quantum computers are so exciting in so many different ways. Not only can they compute multiple functions at the same time, but they use the laws of quantum physics to operate, which makes simulating really complex molecules much, much easier. So there are a couple of different algorithms that are actually being used to revolutionize the drug discovery process today. One of which is the Quantum Approximate Optimization Algorithm, or QAOA for short. See, QAOA is an approximate machine learning algorithm, which means it doesn't always give us the best answer, but it gives us the good enough answer, which in the case of solving some really complex problems is, well, good enough. So the main goal of QAOA is to find a given bit string Z that maximizes our function C. So basically what we want to do is find a combination of zeros and ones that is really, really close to the optimal answer, so the ratio gets closer and closer to 1. So the way that QAOA does this is by using a classical quantum hybrid algorithm. And this is actually one of the reasons why it's so desired today. Since quantum computing is still in development and isn't all the way there yet, by using an algorithm that uses equal parts quantum and classical circuits, we can promise results for the near future, especially in drug design. So first what we want to do with this algorithm is initialize two variational parameters, gamma and beta. Then we want to feed the quantum part of the circuit some qubits that have been in superposition, and we want to apply these two operations onto our parameters. Next, we want to measure the qubits in which the parameters are stored in and feed them to the classical part for optimization. We then repeat this loop over and over until we get our solution. Now, every time we iterate through the loop, we actually get a better and better answer. And the algorithm actually does this by solving this equation. Now, I know it looks like a bunch of jumble right now, but basically what we want to do is maximize the function fp with the parameters gamma and beta. So essentially every time we go through the loop, we get a better and better answer. So QAOA actually specializes in solving the max cut problem, which unlocks a whole new world for quantum machine learning. So the max cut problem goes a little bit like this. Say I have 4 different vertices and I have edges connecting every single one of them. Now I can paint each vertex either red or blue. Now let's say for every 2 dots that are differently colored and are connected, I get a point. What color should I paint every dot so I can maximize my points? Well, in this case, this is going to be the correct solution because I get 4 points and that is the maximum amount I can get for this game. But what happens when I start adding weights to those edges? So instead of every single edge being equal to 1, let's say the ones in the middle are worth more and the ones off to the sides are worth less. Now this is going to be my optimal solution. Instead of getting 4 points, I get 16. Now I know this problem may seem a little trivial right now and it doesn't seem very useful, but solving this problem actually unlocks a whole new world in quantum machine learning. So what I did is I took this max cut problem to cluster a group of data. So I actually used, for my input, I used sepal and stem lengths of 2 different types of flowers, and I plotted the data points on a two-dimensional graph. And then I connected every single data point to every other point to create a max cut problem out of my data. Now, for the weights, I computed the distance between every single point to every other point, so I could get the weights between every single point. Now, as we saw before, we know that when we have larger weights in the middle and smaller weights off to the side, this is going to be our correct solution. And now, since we know that when we have two different flowers of the same species, they're going to have similar characteristics. So they'll be much closer to each other and much farther away from a flower with different characteristics. So what I did is I ran my data through the QAOA algorithm, and I got this as my answer. But since we're dealing with computers and not colors, instead of being painted red and blue, they're given the bit value of 0 or 1. So virtually just by solving this max cut problem, I clustered a group of data. And going back to the beginning, how we wanted to find that special combination of zeros and ones that optimizes our function c, we know that our answer is going to be 0, 0, 1, 1. And that's exactly what the algorithm outputted. Here you can actually see a visual representation of the clustered data. So, what? Now, I know my program isn't too useful to anyone, and it doesn't really do much. But the real potential is unlocked when we scale QAOA. See, there are a bunch of different companies that are actually leveraging the power of quantum machine learning to solve some really complex problems, one of which being protein cure. Now, protein cure is actually using algorithms, just like QAOA, to simulate the folding of proteins to develop new drugs. Now, instead of having a researcher test thousands upon thousands of different compounds over the course of 5 years just to narrow it down to a couple suitable candidates, Protein Cure plans to design the perfect drug from the beginning and using QAOA to optimize its properties. Now, we won't have to wait 5 years for a new drug, but we can shorten the time down to maybe a few weeks or even days. Quantum computing obviously offers a lot of promise in the domain of drug discovery. And now, not only will we be able to bring new drugs to the market sooner, but hopefully I'll help my mom find what she wants to wear in a shorter amount of time.